So this is about pitfalls in teaching programming. Most of you are teaching programming or have been teaching or TAing programming. We said we have different languages. Languages listed just a couple of minutes ago were Java, Python, C, and Racket. And then I said there is one thing that has been shown that programming is actually difficult to learn. This was this rainfall problem. It's basically a list of values, of numbers. A study was done at Yale University, and they found in their bachelor program in the first year, only 17% of students could implement this thing, given the spec that you see here, without mistakes. So that's kind of discouraging. Now, learning to program is hard. This was one study, but it has been repeated this was after the first term, then they did it after the second semester. It went up, but that's after a year. You would expect that students can do a for loop or a while loop. And in the end of the bachelor, essentially, 2/3 were able to do it at Yale. Then they said we need to redo this quite a bit later, like almost 20 years later. They did it across many universities in different countries. They found after 1 year only 20%, 21% could do it. They did it in yet another study, bigger context, more universities. They got a bigger percentage who were able to do this. 2013 is the most recent one. They did it again, and they found quite big numbers you could be happy with. But what it says here is with scaffolding, and what does scaffolding mean in this case? It's a term in education where you help people, and here you help them by giving them unit tests. So the students essentially were writing code, didn't maybe know exactly what they were doing, compile, it compiles, run the tests, tests pass, I'm done. So that scaffolding is very helpful in a way, educationally not so helpful, because if you take it away, they can't do it. So you get back down to 32%, down to 12%, which is very, very discouraging. And this is not one of those thousands of education papers where you see a small study in somebody's personal classroom, but this is really broad. Let's get rid of this. So what I'm going to try to talk about is 4 pitfalls, and the pitfalls are here. For people who are in the Racket universe, most of those things will be very yes, of course. For those of you outside that universe, you may say, well, I disagree. I hope I can convince you a little bit. I'll go into each of those 4, give you a very high-level intuition of why I believe this was a pitfall, this is a pitfall, and we can fix it to some degree. First pitfall is this. Can you answer the question? Who has an answer? Let's do humming. So if you believe the 2 colorful points touch at some point, hum now. Humming means okay. If you believe they never touch, hum now. You guys are good. Okay. So I programmed it, and I know they never touch. But let me ask the question again. If you believe here, on this picture you see, those 2 points touch, hum now. Okay, it's absolute quiet. It's absolutely obvious. It's totally clear. There's no discussion, no thinking about whatever is the trajectory and did they ever touch? Maybe they moved out of the screen. Nothing. It's clear they do not touch. So if you taught, I don't know, computer graphics, physics, particle simulation, whatever, wouldn't you first want to explain this thing here and only afterwards go here and say, now let's talk about time and things change over time? And if you translate that into computer science, wouldn't you first want to talk about the immutable stuff before you start to talk about things that get mutated, states, variables? I think we should do this first. It's simpler. And once you understand this, you can then say, now let's tackle time. And that's what Carlo Alberto does. That's what the course PF1 does, not PF2. I do the wrong thing, but yeah. So one should start with this. This was targeted at high school teachers, and those high school teachers all teach Python. Pretty much all across Switzerland, they teach Python. And they teach, the first thing they think about, variables, loops. I think it's not the right thing. So I believe, and I'm kind of regurgitating, it's not my own invention here. You read the book that we use in PF1 and you can feel this. You read meta-level discussions about that book, and it's clear that this is a point here. So it's not like my invention. But we should exploit that feature that we can first talk about static structures in multiple things. And how can we do that? Well, we could pick a language in which we at least can represent immutability in some way, and that's not Python, because there even pi is mutable. So if you ever have a program and you use pi somewhere, check that it actually is 3.14 and so on, because it's easy to change it. So you want to have a language that maybe supports const like JavaScript or final like Java or something like that. Even better, you have a language that doesn't allow mutation at first, and that would be BSL, beginning student language. And then you move on and you introduce mutability. That was the first. Second pitfall. What brand is this? Now, if you're Swiss, you have to know. So Aaron, you know. Okay. If you're not Swiss, especially Italians, I was very surprised to learn. Luca is like, So who knows what that is? It's only, yeah, now Igor knows too. So I grew up with this thing, and this was like, there are two brands of toys, and it's very obvious they're on the same level, but I discovered, no, this is not. And I think there's a reason. So this is Playmobil. Now, let's look at the other brand of toy, this one. Who knows this one? What is it? Yeah, Lego. Okay, so we have Playmobil and we have Lego. Now, for you, this doesn't work. For the Swiss high school teachers, this was brilliant because it was clear. They all said, having experience playing themselves with the toys and having bought the toys for their kids, like personal kids, not school kids, it was very clear they all said this one. And there's a question, why the heck would you say this one? So for you it doesn't work, maybe for Aaron it works, but the rest is kind of pointless. So I'll get back to this. Here's a quote. It's a quote that actually is not from a computer scientist for one. So the acts of the mind wherein it exerts power over simple ideas are chiefly those three. And I'm only going to show one of those three. And that one act of the mind is combining simple ideas into compound ideas. And this way you can build everything. So composition. Who could be the person who's made that statement? It's not a computer scientist.
Yes, Descartes.
Descartes, yeah. If I gave a longer talk, I would shoot down Descartes later on. Could be. It was this guy. I would have no clue. I think it was Luca who found the quote. It's beautiful, I think. It's John Locke, philosopher, about human understanding, so it kind of fits, no program understanding or whatever. So this guy said in 1689 that we should decompose things and we should use composition to build things. And things are independent and you compose them to build nice things. Now, I'll do a little jump. Natural science, we're all built out of stuff, and apparently 70% of my body is water, and then there's some other stuff. If you look at programs, code, source code, you could also highlight a big chunk of that code, and it's also blue here. What is the blue stuff? Expressions. If you did the little activity I pushed upon you, so those are expressions. And Luca and Igor did some studying and found that in something like 88,000 projects that are student developer projects, not GitHub, but it comes from the black box data set, which captures everything students do in BlueJ, which is an educational IDE for Java. In there, about 53% of tokens, of source code tokens, are dedicated to expressions. And there's a lot of expression stuff. So there's another quote, this time from a computer science group. Programming language should be designed not by piling feature upon feature, and that is really Playmobil, where you have not simple components, but you have a million different pieces. Like if you have a wall piece for a castle which has flowers attached to it. It's one thing. You can't buy flowers and the wall and then use the wall to build another kind of house. It's the castle wall for this place in your castle. Very, very special purpose. And so you need lots of those things. But by removing the weaknesses and restrictions, so make things simple so that you then can compose them and you don't need all those features. And then they argue, of course, Racket or BSL or Lisp or Scheme, languages like that, they're very small. They have very few rules you need to learn and understand, and you can form expressions to build anything you want. And that's really our Lego pieces. So it's not really true. It's simplified. If you buy Lego today, I bought for my kids, there's also a million pieces that are all special purpose. But you can still buy boxes like this. There's nothing but those very, very basic building blocks, and you can build everything from them. So that comes from, obviously, some kind of Scheme report or Scheme document pitching that language. So what I pushed you into, this is kind of trying to get across the idea of composing code from small pieces and to have orthogonal things you can combine, mix and match the way you want. So you don't need to learn exceptions. Like when you learn French, when I had to learn French, I had to learn millions of exceptions. I never managed. My French is totally broken. But if you learn BSL, there are like 20 rules and you have the whole language. No exception at all. It's so much simpler. So here is an example from kind of how Python is sometimes taught. So people say, okay, let's talk about conditionals. So you can have, if you have more than 100 francs cash, you buy the article. Or if you have more than 100 francs cash or you have credit, you buy the article. Or if you have more than 100 francs cash and you cannot resist, or you cannot, and you cannot resist, I guess, you can buy the article. So they have those examples, and those are like Playmobil pieces. They're like big chunks. And what really students, and I found sometimes professors or teachers believe, is that this is a atomic piece. You cannot break this apart. It's like an if needs to have this thing here, or also less than. Maybe you can have an equals, but this belongs together. It's like one thing. And then and not is a thing. They believe and not is an operator. It's like, what? Really? I mean, have you ever seen not, like you can negate or invert or whatever? So this is Playmobil thinking. And I think we should talk about it in a compositional way. So you say, and if it's some decision point, and then you have an expression you can build using your Lego pieces. You can build that together however you want. They're separate ideas. You do composition. You don't need to learn 100 rules. And then you have to, of course, talk about the Lego pieces. And those are the green blocks you've seen in the expression tutor. You can combine them together to make any expression that you possibly could have in your programming language. Now, in that paper, Luca and Igor went, and I think that part was just Luca, went to textbooks that are used today in teaching Java at university level mostly. I think it's 6 textbooks that were updated within the last 10 years and that were used in another study as a source for looking at how things are taught. And read the chapters and sections that talk about exceptions to see how are expressions, and they looked how are expressions explained in those books. And then there were things like this. So there was a piece of code to explain this is a way how you can play with arrays. And you need to write the name of the array and then square brackets and then some index. So that's not a good way to explain this. What goes in front is not the name of an array. You can put anything in front. It's a hole. You can plug in what you want. So the real concept is this. There's a hole in front, there's a hole in between, and you plug in whatever you want. Or here, this was typecasts. Behind the cast, there can be a variable or an expression. Why? There can be an expression. If I write a variable, that is an expression. So I don't need to learn two concepts. This is not a special case here. So it's a whole. And last but not least, this is maybe the most contrived one. So you have allocation of a Pac-Man object somehow, and they say this operator here associates the object that you make with the name in front of the equals. That's also not true. And our students truly tell us when we do tests in PF2 that objects have names. They say that you cannot write new Pac-Man dot something else. They say you cannot write new Pac-Man and put it as a parameter. They really look at this as an atomic thing. And they have so many atomic things they need to look at, they lose track of them. So this is textbook explanation. So those are often misleading, and especially they have a lack of looking at those things as composable pieces, Lego pieces you can put together the way you want. We looked at many misconceptions over the last couple of years, and we cataloged them on this website. And 48 of those misconceptions are about expressions and the composability of expressions and misunderstandings with respect to expressions. So this is really prevalent, and it causes harm or it slows down learning. So here my point is, let's try to be kind of composable. Don't teach a million special pieces, but teach a few general rules and pieces, and then they can build whatever they want. Okay, and how do you do this? You want to explain it. You can, for example, use those little expression trees to play around. That's one way, or you can just talk about it like that and say, look, there is this construct, and you can compose things. Third pitfall. What did Mama say? Yes, life is like a box of chocolates. And what's the next sentence? Yeah, you never know what you're gonna get, or something like that. So what's the name of the movie? Forrest Gump. Yeah, you have to watch it. I liked it. I haven't seen it forever now, though. So why am I showing this? I want to show you a box of chocolate here. I don't know what it is exactly. It could be one you can buy in Coop or Migros. Now I ask you a question. Can you say which type of chocolate was in that place, in that position? And let me show you two choices. Who thinks that it was this guy, Ham? That's clear. No? Who thinks it was that guy? Yes. So why do you know this? Let's look at another box of chocolate. This may be Sprüngli from Zurich. You can get it at the airport if you fly home. What was in this one? I give you two choices. Who thinks it was this one? Who thinks it was that one? Kind of a faint one. It's not so clear, no? Why do you not know it? Because the box here, it has this fluffy thing here that you can shape in whatever way you want. It's very dynamic, or you can say, you can actually put in this anything, a heart, a square, a circle, doesn't matter. So where am I heading? What's the topic here? Types. Okay, so we have a type system here. If you have a language, especially statically typed language, you can assign types to program constructs. So you have a variable, you can say the variable has that type. So this little container there, it has a type. So you can only put values or chocolates of that type in that container. Or if you have an expression you put together, if you're statically typed language, you can give a type to every node in that tree that the expression really is. If you have a function, you have parameter types and return types, and so on and so on. And every value you have in your program also has a type. So if you use a language like Python, which is kind of dynamically typed, if you think about types at all, I mean, you can now have type annotations in Python. And if you program Python, I think you should use them. But if you look at this code here, which could be student code, what's happening here? It's kind of neg A, return -A, and then I call neg pizza. I mean, you don't know much. I mean, you're too good. You already immediately spot probably the type error that's happening here. But the language, normally you save your code and then you run it. And maybe that function is called. Maybe this is actually executed. Maybe not. If it gets executed, it will crash. If it's not executed, you have a bug, and then the train stops running, maybe, I don't know. So that's dynamic typing. Now, that's this thing. You don't know what was in there. A is the little container there. It could have a string in there. It could have a number in there. If it's a number, you can do the negation. If it's a string, you cannot. If you have static typing, then you specify what you have here. You have one of those shapes, and you say it takes an int and returns an int. And then your IDE is going to show you that this doesn't work. You're passing in a string, and it expects an int. That's a type error. It never runs. It never compiles. You know for sure. No bug you need to test for. It just is not going to work. So if you think about education and learning to program, in the learning sciences, there is this idea to give feedback to students so they can learn. And the idea is to give them timely feedback, not you do an exam and then 6 weeks later, like sometimes me, you return the graded exam and they will get the feedback and they will be like, oh, I don't even remember what we did 6 weeks ago. So it should be timely. So you don't wait forever, you do it relatively quick. Now there's a caveat, I think you can do it too quick. So but here I'm not thinking about that. I say quicker is better here. If you do static typing, the feedback comes quick before you even run the program. Dynamic typing, it comes maybe while running, maybe never if that code doesn't get exercised in that specific way. If you want to learn about other advantages of static typing, use Igor's favorite book, Types and Programming Languages by Benjamin Pierce. Yes, Igor, I need to say this is mandatory here. He gives several points why types or static typing are good. They help you find errors early. They help with abstraction because people read only the type signature of your function or method or class or whatever, and they don't need to read the implementation. The signature gives already a lot of information about the semantics. It doesn't give everything, but it gives a lot of information. So it's documentation as well. It helps with safety. You don't have those weird crashes randomly. You can prevent them. The language guarantees that it will not happen, this kind of strange crash. And it could even help you with efficiency. If the compiler knows the types of things, it can compile it so that it's faster. It knows it will be a number. It doesn't have to say at runtime, is it a number or a string? That's better. So if you have this choice and you want to teach programming, you probably should teach statically typed languages, which is the one point against using BSL, which doesn't have explicit types in the language. It's only comments. So exploit this, how, use types. Even if you teach Python, use the type annotations. They're actually nice. There are really strong type checkers out there. If you use VS Code for Python, you get beautiful error messages while you write things if you use types. Last, Pitfall. Now, for the teachers, basically nobody said yes here. For us, PF1, yes, which is, I think, good. Here, I want to make this little detour. I think if you've been to the US recently and you're not American, you don't have some permanent residence or whatever, you need to go through this brutal thing here. And he looks at you, and then, to me, this happened, actually. He said, what's your job? And not in a nice way. And I'm like, okay, I'm in computer science. What was your first program? I'm sorry, sir. I don't remember what my first program was. I started programming when I was in school. I really don't remember. I know. Okay, I know you know a lot about me, but I don't think you know that. He said, no, I know. Hello, world. Okay. So essentially now I'm going to ask you, or I would ask you, what was your first program when you taught recursion? So maybe given that you didn't teach recursion, except for Carlo Alberto, who uses the right book, so it actually does the right thing, but everybody else, you learned recursion at some point. What was the first example? Okay. I guessed it. And that's not me. That's, again, I'm just stealing things from others. Yeah, exactly. It would be exactly like that. So that's wrong. Okay, you're doing it all wrong. Here is an argument from 1996. Programs accept data and produce data. I don't know about you, but when I learned programming in the Swiss-German system, they talked about the EVA principles, or principle that was Eingabe, Verarbeitung, Ausgabe. So input, processing, output. That was like the main thing, and this is exactly that. Processing is the program, it does something. It does something to some input, some data that comes in, and it produces some output. So that's what Friedman and Felleisen say. And designing programs requires an understanding of the data, the input and output that they need to produce, right? You have input-output examples, and then you think, how can I write an algorithm that does the right thing here? So the data drives your design of the algorithm. The good program reflects the shape of the data it deals with. So if you know the data structures, if you design the data structures, then writing the algorithm for those data structures is not so extremely hard anymore. It gives a lot away. Now, there are a couple of points which are specific to recursion, and they motivate essentially HTTP, the book Carlo Alberto uses. Most collections of data and most programs are recursive. Now, that takes a worldview where you think about data as a recursive structure, which actually is quite, I think, quite natural. I'll give you a couple of examples then. And recursion is defining an object or solving a problem, so data and algorithm, in terms of itself. Now, what would be good first recursive programs you would write if this holds? So if you think that data drives everything, would Fibonacci be a good example? Would factorial be a good example? What is the data? What is the structure of the data? If you're a mathematician, you will find the structure in the integers, and you say, well, actually piano and whatnot, and you can think about the structure. But our students are not thinking like that, I believe. They see a number, and it's an atom. There's no structure in there. And then they have to come up with a structure for the computation, and they have no data to attach their thinking to, which is hard. So you should start first, I believe, and that's what we do. You should think about the recursive data structures, you talk about them, and then you can do a program over those structures, a recursive program over a recursive structure. And what's the most obvious structure that every kid in school would know? It's my mom, my dad. They both have a mom and a dad, which have a mom and a dad, and it goes on forever like that. Family tree. Or if they have done stuff like our students on a computer, you can talk about the file tree that they see in Explorer or in Finder or whatever. And you can ask them, can I create a directory in a directory? And then can I create yet another directory? How deep can I go? And they'll figure out, oh, actually it's unbounded. Another one, also for more adult people, a management hierarchy. You have a manager, the manager has a manager, it goes up until the CEO. Or an example I use now in PF2 often is a linked list. So you come to an amusement park, Disney World or Europa Park, and there's a very long line. You approach the line from the back, so you come here, and you want to know how many people are in front of you. Today you have a sign that says 5 minutes wait or so, but assume there is no sign, and you want to know. You could try to follow the line of people and to count like this, but you cannot actually do that. They don't let you go there. So one way to do it is to ask the person in front of you, how many people are in front of you? And then this person asks this person, and so it goes to the front, and then you get nobody, 1, 2, 3, 4, 5, 6, 7. And that's a recursive computation over a recursive data structure, over a linked list. Or you can talk about social networks. Everybody knows not Facebook, but Instagram or TikTok. You say, how many friends do you have? Do your friends know you? And you have a cycle, and you can talk about all this recursion in there. And then say, now we do a depth-first search on our graph and find stuff. So the point is, if you do recursion without support structure, it's really hard for students to do, and everybody says it's really difficult. We cannot start with recursion. Using HTTP is the wrong approach. You need to do loops first. They're much simpler. I think that's not necessarily true. And I see it a little bit like this. So this one is if you have a data structure that supports you, and what you need to do in the recursion is just go from one step to the next, and you follow the data structure. And this one is if you do recursion without data structure, so Fibonacci, and you don't know where you're going, how far, when you're done, it's all kind of generative. So why should we do Fibonacci and factorial first? Let's do it the right way. Let's talk about data structures and then do the computation. I'm pretty much done. One more, Pitfall, fifth. Didn't notice that, mentioned that before, but I need to mention it. This one. Who doesn't know it? I think everybody needs to know this guy. It's our Copilot. And I haven't put that in that slide, but I came up with a new term, and I think we need to make that a meme or a keyword, a hashtag or something like that. So if you talk about GitHub Copilot, you have the captain and you have the Copilot, and you're supposed to be, as a programmer, you're the captain, and the Copilot helps you, right? Now, when I saw our students in PF1, I mentioned it to Carlo Alberto. I was in the cafe next to the Mensa with Luca and sitting there, and he says, "Oh, they're using Dr. Racket." I was like, "Yes, they're working on their homework assignment, PF1, that will be really great." And then he says, "I see they have VS Code and Copilot open, and they're tabbing through to get the solution to the programming problem." So I think instead of saying, "I'm a programmer" or "I'm a captain," we should create the term tapton. You're tapping, that's it, tapton. Okay, I need to tweet that somehow. So this is now free for students, luckily also free for us. So we have the equal, like a parity of power somehow. A few weeks ago, it was not free for educators, only for students. So you couldn't even try what they get as a help. So to solve this, we need bridges to help overcome those pitfalls. Immutability, you want to talk about things being immutable and composing things with immutable things. Ignoring expressions, you want to explicitly talk about composability of expressions. Types, you want to do static types. Data structures. So we build tools in our group. One of the tools is the one that I pushed a little bit for you to try out, Expression Tutor. And another one, which I didn't mention, is PyTamaro, where Luca developed a nice library in Python that's basically ripping off HTTP's image toolkit for those to teach pack, for those of you who went through PF1 with HTTP. But it's for Python. So it's a library to do algebraic compositional graphics by composing needle images. It's, I think, better, but more limited than the one that's in the teach pack. There are some nice properties that make it beautifully composable. So this helps with immutability because it's completely immutable. You build images and you compose them, and you can never change anything. If you have an image, that's it. You can compose it with other stuff, you get a new image. Expressions, you use that tutor. Types, you can actually annotate those expressions, and it can automatically check it. It can automatically give you the solution. For static typing in Java, we're working on doing the same for Python now in one of the MSDE theses. And last but not least, with PyTamaro, you're talking about the data structure. You're building up this kind of scene graph or tree, and if you then wanted to do computation, you might be able to do that over that. So that's my pitch. I think there are pitfalls. There are solutions. They're not solutions, but they help you or us to get closer to this. That's all I had to say.